Okay, so this is, you guys, this is going to be part 2 of your lecture. Don't want to scream. Okay, so a water molecule. Let me steal that from you. So a water molecule, the bonds are at fairly close to a right angle. Not exactly a right angle, but you guys see kind of an L shape. You guys with me on that? Okay, now, when I gave you the little magnet models, you saw, let me see somebody else's water molecule. Awesome. You saw that the hydrogen side was attracted to what side of another water molecule? The oxygen. So then they lined up. That's because the oxygen side has a charge. Does anybody know, positive or negative? It's negative. And the hydrogen has a positive side. Now this uneven distribution of charges is called polar. Okay, shh, you guys, we are videotaping, so all your little sounds and stuff are being picked up for others to hear. Okay, so once again, water is polar because of this difference here between the uneven distribution of charges. Now, how does this compare to your methane model? Let's see those methane models. And you have to remember these models are lame in the sense that they're not showing movement, right? Also, your water molecule did not show the attraction that the magnetic models did. That was a little bit better of a model because it was showing more realistic properties. So this thing would be spinning around. Do you think the charge would be evenly distributed for that molecule? That is true. So it's not polar, it is known as non-polar. Okay? So I wanted you guys to see that with those models. Go ahead and take your models apart. All of them. And let's just put the stuff nicely away in the kit, cover it, and we'll come back to some models later in this lecture. So this slide is talking about your hydrogen bonds. The attraction that you felt with the magnetic models, let me show you that. This attraction with the magnetic models, you guys, you can see that the oxygen side lines up with the hydrogen side. That attraction, that pull is called a hydrogen bond. Okay? So that's what a hydrogen bond is. The attraction between a positive hydrogen. You guys, I need everybody's attention. I don't want this being recorded like this. And it's being recorded like this. Okay, so join me. If you're talking, you're being distracting. The lecture is being recorded right now for people to watch. Okay, so anyway, there's just that attraction between the hydrogen positive charge and the negative oxygen charge is called a what type of bond? Beautiful. It's a weak bond. They're not sharing electrons. It's just the attraction of the opposite charges wanting to be next to each other. Okay, now, back to ionic bonds. We talked about ionic bonds in the first part of this lecture real quickly. I want to bring it up a little bit more, though. I said they're your strongest bonds, but under conditions of a solvent, like water, the attraction can easily be broken. What happens to salt when you put it in water? It dissolves. Okay, you guys should have your kit already put away. You have a pen or pencil. You being able to use a pen or pencil so that you can add things. So water is all over our earth. We had talked about it last time too. It's all inside you. Okay, you're not made of water, but you're full of water. Okay, so all this stuff gets dissolved in water. Okay, and the ionic bond, when they break in water, they form ions. You could see the sodium charge and the calcium charge. That also happens with the hydrogen charge and the OH. So water itself is not always completely bonded. Sometimes there's extra free hydrogen ions in solution. Sometimes there's extra OH ions in solution. And that has to do with this important scale. What's the name of this scale? pH scale. Now, it is very important for you to realize that that capital H in pH right here is referring, yes, I heard it, awesome, referring to hydrogen. So there is a pOH scale, and it would be the opposite, okay? The pH scale goes from just above 0 all the way to 14. Okay, now, the acidic numbers are the lower numbers. Anything less than what? And the basic is anything above, right, maxing at 14. Okay, now, the other thing I want you to realize that the farther they are on the scale, either the lower or the higher, the more dangerous they are to you, because the more ions that they have in them, and it's not balanced in there, so those charges will rip other things apart. So you put stuff in real acidic things, like cotton shirts, it's going to rip the ions, it's going to rip the molecules apart and make holes in it. On the other end, the OHs will do the same thing, because they're of that unequal charge in the solution. When, I was going to tell you guys. Okay. So anything very far from 7 is not good for living organisms. So here's some typical examples here. The sodium hydroxide is very, very dangerous. Oven cleaner, you feel this, you guys, when you use it. You breathe in, it burns your nose, it burns your eyes. It's not comfortable because it's not good for you. Okay. Same thing happens down on the acidic side. You guys know, like your stomach acid, right? It's about a 3. It's pretty acidic. That's why when we get sick, if we're vomiting, does our throat start hurting from that? Yeah. Or even sometimes when we have a good burp or something, you could get that acid right there. Okay? Yes. Okay, so then the idea of acid rain, right? So we release some things like nitrogen gas and sulfur gas, and we get that up in our clouds, and with the sunlight and the water up there, we get a more acidic rainwater. And then it hurts the things, like you could see these trees here. It also gets in water, and then it kills fish. So it's not good for us. So again, we like neutral. Okay, now we're moving on. This is a big step right here. This is one of your learning targets. You guys don't have a learning guide yet, do you? I will get that to you next class. So one of your learning targets is to know the 4 macromolecules that are in us, are part of life. Okay? So I talked to you guys last time about carbon molecule. You could see here that it's easy for carbons to make long chains. It's easy for carbons to make branched chains, where they have a long chain and branches off. All these will change the structure of the molecule, and therefore the function of what the molecule does. These are carbon molecules here, each of these angles. It's a simpler way to write it instead of a big messy thing right here. And they make rings. So carbon can make lots of varieties of molecules. And it does. Here's another picture again. And we will make a carbon molecule here in a minute that's longer than the methane one, where we start linking the carbons up. But you can see that these are 2 different models here, and you can see a lot more in this model than you can in the stick model or the flat model. Okay, so the 4 macromolecules that you need to remember are, the first one is carbohydrates. Notice that all carbohydrates have a 2 to 1, let's see here, it's actually a 1 to 2 to 1 ratio. You can see 6 carbons to 12 H's to 6 oxygens. I'll fix that for you guys. And it's very important that you know the functions of carbohydrates. So what are they, you guys? And this is mostly for animals. Well, for all organisms, they definitely do provide energy. In plants, they're more famous when they do their structural function. Okay? So we'll talk more about that, like cellulose, for example. Okay, now let me make sure I have this right. Contain carbon atoms and hydrogen oxygens to the same two. That doesn't make sense, right? We want a 1 to 2 to 1 ratio. So fix that. A 1 to 2 to 1. I just left part of it off. So there's 1 carbon to every hydrogen. There's 2, and then back to 1 oxygen. Okay, the simplest carbohydrate is called a monosaccharide. Mono means what? 1. So then there's these little more complex would be a disaccharide. What do you think the di stands for? 2. Now you have, these are monosaccharides, for example, glucose and fructose. You can get these guys to bond together. The H will come off here and the OH will come off there, and then it'll bond together. So right here to here. Okay, now we're going to do that. We'll show you with a stick and model. Since we're losing an H2O, it's called a dehydration reaction. All of these macromolecules are built by dehydration reactions, okay, by losing water. So those are disaccharides. Then we get these huge polysaccharides. And now to get all the monosaccharides to link up into a long chain, okay, like this is glucose, glucose, glucose. It lost an H on one side and OH on the other. Then there was an opening, and we have long chains. This is just a little example. It would go on and on and on. Now this is when it's good for structure, because you have a long stringy-like material, cellulose, that supports plants. They could break it down if they need it. Plants also make starch. Where do you guys find starch? Yeah, yummy potatoes, saltine crackers, all that sort of stuff, which again is a polysaccharide. Same thing with glycogen, and that's another polysaccharide. Okay, so let's stop here, and we'll work with, what do we have, 5 minutes? Let me just keep going, and then we'll work with our kits next class. So the second type, if you want to number these, number 1 was carbohydrates, number 2 is lipids. This is your second out of your 4th type of macromolecule. Okay, so lipids are fats and oils. They're also large molecules. That's why we're calling them macromolecules. What do you think their function is? Oops, my fault. So do they store energy? Do carbohydrates provide us with energy? But they don't do a really good job storing it. In plants, the starch does work in plants. But in animals, we're talking about long-term storage fats, right? But also plants, that's where we get our vegetable oils from, right? Canola and all that. That's their long storage molecule. What else? Carbon and building of structural parts of cell membranes. These are 2 very different functions. The actual macromolecules also look very different, okay? So I'll show you in a minute. So let's first just talk about lipids, fatty acids, glycerol. Those are your simple fats. Now think back of that polarity. I'm going to show you a picture, but do oils like water? They don't mix. It's because the oils, are they polar or are they non-polar? They're non-polar. So they don't want to be near the water. Now, they contain carbon, hydrogen, and oxygen, just like the carbohydrates, but are they at the same fixed ratio? No. Okay? So let's look farther. So here is a typical lipid. It's called a triglyceride. And its reason it's called tri is because it's built of 3 fatty acid chains. You see that? And it's attached to a glycerol. And so this is what a lipid looks like right here. It's this glycerol. And if we were simply, again, it's a dehydration thing, so we're going to lose and we're going to bond on here with these different fatty acid chains. Okay? Is this a fat or an oil, you guys? Yes, you need to remember that. So triglycerides are fats and oils. So what's their function? It's to store energy. Okay? So we're continuing here. Oops, maybe. Okay, I want to get to the difference between unsaturated and saturated. You can see on the bottom of the slide there, you have something different than on the top. Here is saturated. What is different from this fatty acid chain and this fatty acid chain? There are double bonds. Now, the model of this drawing is, again, not that good, because if those double bonds are going to pull it closer, you're going to get a kinked fatty acid. And we can also do that with our stick and models. We'll do that next time. Whereas the saturated, it means saturated. It's full. It can't hold any more hydrogens. You could break one of these double bonds down here, and that's called hydrogenated fats. We can make them be saturated. But what's cool, you guys, is which one's healthier for you? The unsaturated, because it's a little too basic, but just to give you an idea, it's harder for you to break it down because of the double bonds. And so then you're not pulling every bit of energy out of it. Now, if we didn't have a ton of food, this would not be as good. If we were starving, it's better for us to eat saturated because we can get more calories from it. But if we're overeating, especially if we're overeating fats, then it's better to have the unsaturated because you're not going to digest as much. And one more thing before I'm done. Which one's solid at room temperature? Yes, so give me examples. Butter and lard and shortening. And unsaturated, how do you find it at room temperature? Liquid, like your oils, right? Your canola, your olive oil, and all these things. Okay? I will stop there. Draw a line where we stopped. Review this stuff so you're very comfortable with it.